Let's dive into an example of a question, typical question that's going to utilize the negative binomial distribution. In an NBA championship series, the first team to win 4 games is the winner. First team to win 4 games. This is also called usually a best of 7 series. Best of 7 because the most amount of games that could be played is 7, right? You could have the first team win 3, the second team could also win 3, but then after that, so that's 6 games, then the next game someone's going to win it, and then that's the 7th, and so there's the 4th win. So it's at most 7 games. First team to win 4, also called a best of 7. First team to win 4 games is the winner. So let's suppose we've got 2 teams, and we'll say that team A has probability of 0.55. A has probability of, so 55% chance. Team A has a probability of 0.55 of winning a game over Team B. All right. So let's answer a few parts here. Part A, what's the probability that Team A will win the series in 6 games? What is the probability that Team A wins in 6 games? What is the probability that Team A wins in 6 games? All right, this is a negative binomial probability distribution question. We're looking for the probability that it takes 6 games to get how many wins? 4. 6 games to get the 4th win. 6 games to get 4 wins. The probability for Team A to win is 0.55. 0.55. All right, so according to our negative binomial distribution, let's take a look here. It takes 6 games, so that means that out of the first 5 games, you have to choose 3 of them to win. Out of the first 5, you have to choose 3 of them to win. And then how many games in total are you winning? You are winning 4 with probability 0.55, and you are losing 2. And the probability of losing 2 is 0.45 squared. So 5 choose 3, 0.55 to the 4th, and 0.45 squared. We are just directly plugging that in to our negative binomial distribution that we have in our white box here. X minus 1, choose K minus 1, P to the K, Q to the X minus K. 5 choose 3, 0.55 to the 4th, 0.45 squared. Run that through a calculator. Rounding this off to about 4 places is 0.1853. 0.1853. Part B. What is the probability that Team A wins the series? What is the probability Team A will win the series? All right, well, this is a discrete case, or a discrete problem that we can break out into separate cases. What's the probability that Team A will win the series? We're going to have to look at all the possible cases that Team A could win. So we could ask ourselves that Team A will win 5 4 games. They could win it in 4 games. They could win it in 5 games. They could win it in 6, which we already know. They could also win it in 7 games. And we just need to add up all of those probabilities. So these are distinct, not only are they distinct, these are disjoint cases, right? If Team A wins it in 4 games, then the 5th game is never played, right? If Team A does not win it in 4 games, but they win it in 5, then the 6th and 7th game is not played, right? So we just need to add up the probability that the 4th win comes at the 4th game, or the probability that the 4th win comes at the 5th game, or the probability that the 4th win comes at the 6th game, or the probability that the 4th win, comes at the 7th game. I think you get the idea there. Okay. So we can write out our coefficients here. We'll start to see the pattern. Probability that x is equal to 4. That means that out of 3 games before that, you have 1, 3. Actually, probability that x equals 4, you think about that specific case. If you're winning the 4th game in 4 games, that has to be a win, a win, a win, and a win. So that is just going to be 0.55 to the 4th because there are no losses. What about the probability that x is equal to 5? Okay, so here we can utilize the negative binomial distribution because there are going to be 4 games played ahead of time where you win 3 of them. And then you're going to have 1, 4, so 0.55 to the 4th. And how many did you lose? Remember, our loss probability is 0.45. We've lost 1, so 0.45 to the 1st. What about the probability that x is equal to 6? Well, we already have that above. We have that above. I'm just going to write down the combination and 0.55 to the 4th and 0.45 squared to maybe start to see a pattern here. But we know that's going to be the 0.1853 that we already got there. What's the probability it takes 7 games to win the series? That means there are 6 games where you can win 3 of them. In total, you still win 4 of them. And now you've lost 3. So 0.45 cubed. All right. And so we can just run these through our calculator and try to get each of these approximately as a decimal. So 0.55 to the 4th. I've got about 0.0915. And then 4 choose 3, 0.55 to the 4th times 0.45. 0.1647 is what I've got there. What about 0.1853 for next one? That's the answer we found in part A. And the last one, 6 choose 3, 0.55 to the 4th times 0.45 cubed. I've got 0.1668. And so we add those 4 probabilities together, and that's 0.6083. It's a little bit of effort on the computation there. A little bit tedious plugging into the calculator, but not too bad if we just grind through it, okay? Not too bad. Okay. Interesting. Cool. Nice. What's also kind of cool about looking at each of these individual probabilities is you could answer the question, what's the most likely scenario, right? In this 7-game series with these probabilities of winning, what's the most likely number of games it would take? The most likely number of games it would take, it would be this probability right here. This is pretty close, but this one's higher. And that would be associated with 6 games. So a 6-game series is most likely in this specific scenario, which is just kind of a interesting little thing to think about. All right, part C. What if instead of a 7-game series, it was only a 5-game series? Instead of a 7-game series, it was only a 5-game 5-game series. And if you're not familiar again with the notions here of these series, 5-game series means the most games you can play would be 5. That'd be the first one to get 3 wins then. First to win 3 games. So instead of a 7-game series, it's only a 5-game series. All right. Then what is the probability that Team A wins? What is the probability that Team A wins? What is the probability Team A wins? Okay, well, this is essentially the same type of question, except if it's only a 3-game series, then we're looking at the probability that X would be between 3 and 5, right? But you're only needing to win 3. You'd only need to win 3. So this is a negative binomial question where we can break this up into separate parts again. Probability that X is equal to 3, plus the probability that X is equal to 4, plus the probability that X is equal to 5, but make sure you update your parameters here, right? This is going to be a negative binomial distribution where you are trying to win 3 games and you do it in 3 tries with a success probability of 55%, plus the probability that it takes you 4 tries to win 3 games with a success probability of 55%, and then plus negative binomial probability, it takes you 5 tries to win the 3rd game with a success probability of 55%. And we can run those numbers, get those combinations and multiply everything out and add it together. Probability that X is equal to 3, you should get 0.1664 here. Probability that X is equal to 4, you should get 0.2246. And the probability that it takes a 5-game series is 0.2021. So we add those together, and this is 0.5931. One of the main reasons why I'm having us look at this number here is I want to compare it with the answer we got in part B, the 7-game series. The 7-game series, Team A had let's call it a 61% chance of winning. And in the 5-game series, Team A has a less chance of winning, a 59.3% chance of winning. Okay? And let's try to develop some intuition here. Does this make sense? That the longer series, Team A had a better chance of winning? Well, I would contest yes, right? Think about a 1-game series. What if it was a 1-game series? What's the probability that Team A wins that? Well, if it's only 1 game, Team A wins that with probability 0.55, right? The longer the series, the better it favors the stronger team. The longer the series, the better it favors the stronger team, right? The weaker team is less likely to, quote unquote, upset the stronger team. And so the more games you play, the more that team would have to upset the stronger team, which is a less likely thing to happen. Okay. So this is one of the reasons why, in very important tournaments, things maybe like the NBA finals or Stanley Cup finals, if you're into hockey or whatever, they have 7-game series. The World Series, baseball, Major League Baseball, 7-game series for the World Series. Their goal, the leagues there decided their goal is they want the best team to actually be crowned. They want to identify what the best team is. That's their goal. The longer the series, the better they can do that. In fact, I think baseball actually originally, the first World Series, it was like the Pirates versus, I don't know, I think it was an East Coast team like the Yankees or the Dodgers or something like that. It was a 9-game series. I believe the first World Series was a 9-game series. Even more likely to correctly identify the stronger team. The NFL is a prime example of someone whose goal is not to crown the best team, right? They're all about the upsets. Playoffs, NFL football playoffs, one game, any given Sunday, right? It only takes one game to win. Different goals, very different goals there, okay? But that's neither here nor there. We don't need to talk about tournament scheduling, design, much more. But what I do want to talk about is a specific case of the negative binomial distribution, okay? Sometimes we are interested in the number of trials. Sometimes we are interested in the number of trials it takes to get the first success. Number of trials it takes to get just the first success. Just the first success. Okay, so this is a negative binomial distribution question, but you're looking for just one success, right? So this is essentially just negative binomial. Usually in negative binomial, you're getting k successes where k is larger than 1, but 1's a possibility. And so what does our distribution look like? Our distribution takes x tries to get one success with a probability success of p, becomes x minus 1 choose 0, p to the first, q to the x minus 1. And what is x minus 1 choose 0? Well, that's just going to be x minus 1 factorial over 0 factorial over x minus 1 minus 0 factorial. And so since we have x minus 1 factorial over x minus 1 factorial, everything cancels out there, and that's just equal to 1. And so this really just becomes 1 times p times q to the x minus 1. P times q to the x minus 1. And in this specific case, this is so common, it gets its own name. This is literally the geometric distribution. So in this case, we say x follows a geometric distribution. Geometric distribution with probability mass function g for geometric, x success probability p is p times q to the x minus 1. And since you're only looking at one success, this could happen on the first trial, second trial, third trial, yada, 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 right? The geometric distribution. It's not wrong to say it's a negative binomial distribution, but it's much more appropriate to actually say it's the geometric distribution. We've given it a name for a reason. So many research questions and so many applications use this specific case that it's just much more convenient to refer to it as a geometric distribution rather than saying, oh, this follows a negative binomial distribution with k equals 1. So we'll try to recognize that when we can, all right? But in terms of practice, how does one answer a question involving a geometric distribution? It's a very, very, very similar thing. Very similar thing. So let's just look at one example real quick and then we'll wrap it up here. Let's say that it is known that on average, 1 out of 100 items, 1 out of 100 items is defective. What is the probability that the 5th item inspected, what is the probability that the 5th item inspected is the first defective item? 5th item inspected is the first defective item. First defective item, okay? So in this problem, let's think about what our success is here. Here, a success would be getting a defective item, right? Because we're counting the number of trials it would take to get a defective item. We're asking what's the probability it takes exactly 5 trials to get a defective item. So this is a geometric distribution question, and you're looking for 5 trials. So that means we're going to have success probability. On average, 1 out of 100 items is defective. So P is 1 out of 100, or 0.01. So this is going to be 0.01. Failure probability then would be 0.99, right? 1 minus that. How many failures? Well, the first 4 were failures, right? Failure, 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 times success. Bingo. And so we run that through a calculator. Round it off to 4 places. I've got 0.0096, okay? And so that's your typical geometric distribution question. And it might show up in the middle of a binomial problem, negative binomial problem as well. It's just looking at getting the first success. Something that I guess I could mention that I'm probably not going to go into more detail, though, is the geometric distribution. Because this is a much simpler distribution, if you will, in terms of the probability. P times Q to the x minus 1. There's no combination term in there. Computing the mean and the variance of that is a little bit more straightforward. The mean of the geometric distribution is nice, and the variance is as well. It's just a little bit more complicated with the negative binomial, because you got to think about dealing with that combination term up front. So, anywho, I've said more than enough. I'm going to leave it at that. Any comments, questions, concerns, post those in the discussion thread below, and we will see you in the next video.